Hi folks, welcome to our review session for Statistics Unit 2 exam. In particular, we're going to be dealing mostly with types of probability, things like normal distribution, binomial distributions, and just some basic old probabilities, conditional probabilities. As always, if at any point in time you have a question or you just aren't sure on something, there's a chat box in there. Please ask that question right in there and I'll try and answer it. Please note as well there might be a bit of a delay before when you post it and when I actually see it, so it happens that way. So without further ado, we'll go ahead and get started, and please ask questions. That's the main thing. That's the main reason I'm here. So while at the Mall of America, Consumer Guide reports surveyed 500 people and asked them to list the number of credit cards in their wallet or purse. The results of this survey are given below. So we have the credit cards ranging from 0 to 6. So you have 0 credit cards had 53 people, 1 credit card had 197 people, 2 credit cards had 121 people, 3 credit cards had 78 different people, and then there were 30 people that had 4 credit cards, there were 8 people that had 5 credit cards, and 13 people that had 6 credit cards. Okay. So the first question that we're looking at is, what is the probability that a random person surveyed has 4 credit cards? Now, just a little mention as to what's going on here. We surveyed and we found that 500 people is what we're looking at here, right? So what that means, if we take the total amount, so if I take the total right here and I add up everything in that frequency column, so 53 plus 197 plus 121 plus 78 plus 30 plus 8 plus 13, if we did that correctly, this should add up to 500. Okay, I'm just going to assume that part's correct. Usually, if you're running your own survey, then you definitely want to check that, make sure that that's the case. But for the sake of what's going on here, we're going to say, okay, 500, we agree with what's being said there. And you can double check it and go ahead and check to make sure that adds up to 500. But to answer our question, what is the probability that a random person surveyed has 4 credit cards? So to have 4 credit cards, what are we looking at? Well, the 4 credit cards occur right where I put that star, that row right there. So notice there's 30 people that have 4 credit cards. And then the probability, all we need to do is determine, okay, that's out of how many different people? Well, it's out of 500. So if that's the case, our answer, the probability, so I'll write it this way, has 4 credit cards. That should equal, we take our 30, the total number of people that have 4 credit cards, and divide by the total number of people in our survey. So 30 out of 500. And now some people like to put that as a decimal if need be. Unless it says so, I wouldn't do it, but I'd assume a lot of these problems will say so. This is 0.06. If it has you round 3 decimal places, just put a 0 at the end of it. Keep going from there. Okay? So hopefully that makes sense on that problem. Now, the next one. What is the probability that a random person surveyed has at least 1 credit card? So there's a couple different ways to do this. We can do the long way and the short way. I'll kind of show you both, and then I'll start moving more towards the short way from here on out. So when we take a look, we have at least 1, so that means 1 credit card is a possibility. And I'll abbreviate that with CC if that's okay with everybody. If you have a problem with that, just put it in the chat box and I'll be happy to write it out. But that's one possibility. But we also have to add the probability of 2 credit cards. And we also have to add the probability of 3 credit cards. And we also have to add the probability of 4 credit cards. And we have to keep on going up and up this list until we get to our magical number of 6 credit cards. That's the max that we have listed here. Okay? So what does that equal? Well, this is going to be a nightmare, but that's okay. 1 credit card is 197 out of 500, and hopefully you can see where we got that. We just looked in our table. There's 197 people having 1 credit card, and there's 500 total people. For 2 credit cards, we get 121 out of 500. For 3 credit cards, that's 78 out of 500. For 4 credit cards, what do we have here? That's 30 out of 500. We had that from the previous one. For 5 credit cards, Notice we get 8 people with 5 credit cards, so that's 8 out of 500. And 6 credit cards, that's 13 out of 500. Now, if you add that all up, what do you get? Well, we end up getting, let's see, trying to add all that up in my head. 447, I believe, out of 500. And you can double check my math there. Okay. Oh, and by the way, if you ever, I do make errors with calculators and stuff from time to time. If you see me make a calculator error and you catch it, you post it on here during the chat, I'll give you extra credit for that too. Just an FYI. It does happen from time to time when I'm punching buttons on a calculator. I'm not doing that right now, I'm doing this in my head. But once I do get to points where I'm punching in the calculator, errors happen. It's just a natural part of life. So I try and reward you if you do actually find one. And I apologize ahead of time if it does happen. So always double check is what I'm getting at. So now, this was one method for getting the final answer. Oh, and by the way, you can take that, divide by 447 and divide by 500, and then you should get this thing equals 0.894, right? This was quite tedious, and an easier method, there's a nice little rule of probability. The probability that this event not E occurs equals 1 minus the probability of E. Well, the way we can use that here, so remember this 0.894, I'm going to see if I can come at it a different way, in a much more efficient way. And then we'll try and use that efficiency a little later. When we take a look at this, notice we had to do 1 credit card, 2 credit cards, 3 credit cards, 4 credit cards, 5 credit cards, and 6 credit cards for our probabilities. Well, the only one really left out is 0. And so another way for us to think of this, the probability of at least 1 credit card, if we think about this, this would be the opposite event of that would be 1 minus the probability of 0 credit cards, right? And the 0 credit cards is up on that top row right there. So you have 53 people. So this would be 1 minus 53 over 500. And you can make that 500 over 500. And so if you take that and subtract 53, notice you're left with 447 divided by 500, and which that equals 0.894, which I believe, granted I just erased it, but I believe that's the same answer we had before. And this is a much more efficient method, and that's why we use our probability rule. So we don't have to go through all that addition. And as I mentioned, I mean, there's a possibility where I can make a mistake when I'm adding up all those numbers. Versus just subtracting one thing, that's going to be much more efficient, and there's less of a possibility of me making a mistake. Okay? So that's why we try and be efficient in these methods here. Any questions on that? So hopefully that makes sense on that one. We'll keep on moving along. So now we have another one where we have some sort of layout for us. And sometimes, so this one already has the totals for us. This was kind of nice. So we have in a survey of people in the Savannah area, the following data were obtained relating the occupation and number of credit cards a person carries. So notice down this left-hand column, we have our number of credit cards. So you have 0, 1 to 2, 3 to 4, or 5 or more. And then the top row, so we have accountant, hairdresser, Chewbacca impersonator. Those are the occupations. Okay, and each entry is telling us some information too. So first question that we have, what is the probability that a person carries 3 to 4 credit cards? So notice when we look at this, we have 3 to 4 credit cards appearing here, right? And so we would have to normally add up 75, 350, and 145, but if you notice, that equals 570 right there. Okay, so now how many people were involved in this this scenario? Well, there's 2,670 people where we obtained our data from. So the probability of 3 to 4 credit cards equals 570 divided by 2,670. Okay, and so if we want to make a decimal approximation out of this, I believe we get something like, I had this written down from before. So I believe it's 0.213 approximately, something like that. So hopefully that makes sense on that one. So notice we just went to the row. Now we get into some more interesting problems. What is the probability that a Chewbacca impersonator carries 1 to 2 credit cards? Let's think about that. So what is the probability that a Chewbacca impersonator carries 1 to 2 credit cards? So do we care about hairdressers? Do we care about accountants in this case? Well, no. We are only caring about Chewbacca impersonators. So that is a given piece of information. And with that given piece of information, we have what's called a conditional probability. Okay? So what actually is happening here? We're looking for a Chewbacca impersonator that's carrying 1 to 2 credit cards. So we have a 1 to 2 credit cards, and the way we read this, this is the probability that 1 to 2, the person carries 1 to 2 credit cards, given, is what that little line up and down means, given that that person is a Chewbacca impersonator. That's how you can read that out. Okay, so it's just a shorthand. And that's all the conditional probabilities are. You have one given thing that's already occurred. So now, how do we go about doing this? Well, there's a couple different ways. So I'll show you 2 different ways. One that corresponds to what you might see in your notes, and I'll start actually with the one hopefully that makes a little bit more sense, at least to me, and that would be trying to work with the table. So notice, first off, we have total number of Chewbacca impersonators. Can we find that in the table? Well, yeah. That's right here, 360. Okay, so that's our total number of Chewbacca impersonators, so that's what we're going to put down below. Alright, so now, where do we go from here? Well, the 1 to 2 credit cards, okay, we need to find that information. Well, where would we find 1 to 2 credit cards? Well, notice 1 to 2 credit cards, you could go all the way in this row and go to 645, but we only care about the ones that are Chewbacca impersonators, so the 115. So our answer here is 115 divided by 360. I know that can be a little bit tricky, and I'm going to go through it a different way as well to kind of correspond to what you're seeing probably in the notes. So our answer, just an FYI, is 0.319. Are there any questions on that method? Or if you want to wait until the next method, let me know. I'm happy to show you that too. So the other route we could have taken here, let's talk about this. One you might have seen is the probability of E given F. You get the probability of E and F divided by the probability of F, right? So if we look at it this way, so notice we get 115 over 360, keep that in the back of your mind. So the way to do this one now, how will we go about doing that? Well, probability of E and F. So this would be the probability of 1 to 2 credit cards and Chewbacca impersonator divided by the probability that that person's a Chewbacca impersonator. Okay, so this might be one that you're more comfortable with, and that's fine. So notice, what does it mean? If 1 to 2 credit cards and a Chewbacca impersonator, notice that's 115. And then now what are we out of for that probability? We're out of the total amount, so 2,670. So 2,670. Now, that we aren't done yet, we need to divide by the probability that the person is a Chewbacca impersonator. And notice the Chewbacca impersonator, that's 360 people, divided by 2,670. Right, the total amount. So now what happens? Well, when we take a look at this, Notice that you can do the keep it, change it, flip it if you aren't familiar with fractions and all that stuff. You keep the numerator, you change the division to multiplication, and then you multiply by, you flip the denominator there, so it would be, you multiply by 2,670 divided by 360, and your 2,670s would cancel, and you're left with 115 over 360. Right? So two separate ways to get the same answer. That's what I'm trying to illustrate here. That's something we want to keep in mind. Getting at that answer, doesn't matter which method you use. Find one that you're comfortable with and use it. Right? I just want you to be aware there's more than one way to skin a cat here. Right? So now, moving forward, what is the probability that a person is neither an accountant nor carries 5+ credit cards? Oh, wowzers. So this one actually calls for a couple rules in terms of what's going on. Neither an accountant nor carries 5+ credit cards. So if you were here for that first part, we did one where we actually had the nots involved in one of our probability rules. This one's going to be a little bit trickier with what's going on because we have neither an accountant nor carries 5+ credit cards. So think of it this way. One thing we can do is we could add up all the hairdressers that are not 5 or more. So we'd actually have to add up all the hairdressers that are 5 or more, and then all the Chewbacca impersonators that are not 5 or more credit cards. So basically that's the kind of range, and we'd have to add up all those probabilities. Okay, we can do that, but we have some information that can make this a lot easier on ourselves. So we could find the scenarios of accountants and also on top of that the 5+ credit cards. But in order to do that, we're going to actually have to do a little bit of work. So now notice, with our first case, the number of accountants, right? Notice I'm going 1 minus because it's a neither, so meaning a not here. So if I go the 930 out of 2,670 accountants, and then I'm going to add up the number of people that have 5 or more credit cards, 850. 2,670 credit cards. Now you might think that we could just subtract those parts and we'd be done. But notice, if you were to draw a Venn diagram of just the scenarios with 5 or more, so 5 or more CCs, and then you'd have also the accountants, right? There is some overlap here. In this overlap, think about what's just happened. In the probability, the accountant part, we've counted this intersection once, but when we counted it in the 5 or more, that's the second time we've counted it. So when we've added that up, we've doubled that count, and that count is actually 5 people. So the way we fix that is we subtract off that count, and this happens to also be another one of your probability rules. The probability rule that's going on here, to give you an idea, so we're using it kind of a double context. The probability of E or F is the probability of E plus the probability of F minus the probability of E and F. Okay, so another probability rule into the mix. I know there's a ton of them, right? So when you take that into consideration, notice what do we get here. So we're going to take our 930 plus our 850 and then subtract off 5, and that will give you, notice we have a 1 minus, and then it'd be 1,775 over 2,670. Okay, and so now if we actually simplify that a little bit, let me make sure you can see this too. I'm going to try and fit it down here. If you can't see it, let me know. So this becomes 895 over 2,670. Hopefully, is that better? hopefully you can see it now. And so now when we take this and just convert it to a decimal, you should have something like approximately 0.335 as your final answer. Questions on that piece? If you got questions, oh, got a question? Okay, go ahead, shoot it out there. So I see Meredith has a question. Please, that's what I'm here for. And I know there's a bit of a lag time there from what when you're at a point in there, I might ask you to specify, because sometimes there can be a couple minute delay as well. Oh, okay. Yeah, so you can see it. Okay, so clarify. Thanks, Meredith. So yeah, that's what I'm trying to get at, is making sure you can all see what's going on there and whatnot. And glad to see a chat box is working, so keep them coming if you have comments, concerns, or whatnot. So yeah, let me know. Alright, so let's move on to something slightly different. I'm going to try and mix and match some things in here, so you'll see we'll jump around different topics, because that's how a test can appear. You're not always going to have things in a certain nice order, so I want you to be aware of how this can work out. So, but we've seen some conditional probability stuff, and we'll get back to some more, because I know that was a struggling point. But so here we have below is a partially complete probability model. Enter the probability for the final outcome, and then we're going to find the expected value of the probability model. What the heck does all this mean, right? So there's one thing that we know should happen in a probability model. So you see this fancy symbol, and then you'll see something like probability of X and all that jazz. We have that this, in every probability model, the sum of all the probabilities should equal 1 every single time. So now you see this symbol, and let me kind of highlight this. What happens is people see this and they freak out. They're like, oh my god, what's happening here? Here's all that this means. This is a sum. Okay? And so in our case, the outcomes are 0.5, 1, 1.5, and 4. So to list what's actually happened, here's what they're saying. So with our case, they have the probability that X equals 0.5 plus the probability that X equals, and I'll have to erase this, equal 1. X equals 1 plus the probability that X equals 1.5 plus the probability that X equals 4. All that sum should equal 1. Okay. So now, what do we have? Probability that X equals 0.5. That's 0.35. Plus, probability that X equals 1. That's 0.2. Okay. Probability that X equals 1.5 is 0.15. And then we don't know the probability that X equals 4. We're trying to find that. So all this should equal 1. Okay. So now, moving forward from there, what do we get? Well, if we just add that up, notice our left-hand side is 0.7, so we have 0.7 plus our probability that X equals 4 equals 1. So back from your college algebra days, or math modeling if you've had that, or quantitative skills and reasoning, if I know a few schools offer that. So depending upon what you're dealing with for your course, you can always just subtract 0.7 from the both sides to get 1 minus 0.7, and so our answer is dun 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 0.3 with that sound effect in play right there. Okay, so hopefully that makes sense in terms of the probability model filling in that probability. Notice we're just essentially using the probability rule all over again, that 1 minus business. So now moving forward, we want to find the expected value of the probability model. Okay, how the heck do we do this? Well, this is given. There's a couple different notations. So one, you might hear the mean of the random variable or expected value of X. Both of those mean the same thing. Okay, and what they mean are the summation of X and then P of X. All right. What the heck does this mean? Well, in our case, it's really not too bad. So you have all you're going to do is take the outcome and multiply by the probability. So you're going to go 0.5 times the probability that x equals 0.5 plus, that's what this sigma means, it means sum. So 1 times the probability that x equals 1 plus 1.5 times the probability that x equals 1.5 plus 4 times the probability that x equals 4. Hopefully that all fit on the screen. I'm double checking here just to make sure. I have to check back and forth because they're on different screens, so that's why there's always a little bit of delay there for me to check between the two screens. Okay, so that seems to be fitting pretty nicely. So now let's just fill in those probabilities. So the first one, we have 0.5 times, what's the probability that x equals 0.5? Well, it's 0.35. Okay, we can see that there. And then plus, what else do we have? Well, this would be 1 times probability that x equals 1 is 0.2. Okay. And then plus 1.5, and the probability that x equals 1.5 is 0.15. And then plus 4 times the probability that x equals 4 is 0.3. So now you can just kind of plug and chug and see what this becomes by, you're basically just doing a calculator bit now. And then after all is said and done, oh, and by the way, just a little FYI before I move any further, when you do get a mean, look at your outcomes, and you should always have this expected value to be somewhere within this range. I do see that mistake from time to time, and it kind of baffles my mind. Because if let's say I came up with a number, and let's say I punched in and I got 10. Well, notice our range of values is from 0.5 to 4. And if I end up with 10, that's not going to work whatsoever because it's outside of our range. We don't have a number that would get there in the first place. Okay, so always think your expected value should be something within the range at least. Okay, that's just a double check. So if you do get something outside of the range, you just made a mistake punching something into the calculator. You might have moved a decimal place. So those are good self-checks. Now, I probably should check again, but 1.8 does fall within the range, so we're in pretty good shape. Right? A little FYI, this is not the only way to go about doing this, though. Let me see if I can pull up the calculator and keep those numbers in mind. That's the tricky part, is keeping those numbers in mind. So I might ask for your help along the way if this screen disappears here. Oh no, good. So it's still in here. Awesome. So one route we can do is we can start by inputting two lists. So the first list I'll put in, I'm going to put the outcomes. And so let's see, remember 1.8 is our magical number. So you go 0.5. And then our next outcome is 1. Then our next outcome is 1.5. And then our next outcome was 4. Okay. Now, moving that over, we want to punch in this column. We'll go with all our probabilities. So we had 0.35. I don't know why I punched in the 0, but it does the same thing. And then we can do 0.2. And then we can do 0.15. And then we can do 0.3. So notice first column we put our list of outcomes. Second column we put our list of probabilities. Let's see what happens now. So we're going to try and make a calculation. And so we go to stat and we go to calculate this one var stats. And you might have a TI-84 that displays it slightly different, but same song and dance. I need to hit L1 and then I need to go to L2 as well. And so that's telling you your list 1 is your list of outcomes, your list 2 is your list of probabilities with this one var stats, which is different than the two var stats. And notice what we get. Our x bar equals 1.8, and x bar usually denotes the mean. Hey, and notice the sum of x equals 1.8. Oh my goodness. What do you know? Those things happen to match up. In fact, there is no coincidence there. This expected value of our probability model, you can use a calculator to do all these calculations. By the way, the sigma of x, that's your standard deviation. So you actually have that information as well. It can save you on some of the calculations. But you've seen how we work out the calculations. I want you to be aware of both. Okay. Hopefully that clears the air on that one, and hopefully makes things a little bit quicker for you when it comes down to it. All right, so now we're going to move into a problem. This is going to be a little bit more difficult, but I want to show you the reason we really try and focus on our conditional probabilities, because these are the types of things we got to concern ourselves with. Not necessarily for the Tour de France, but drug testing is a big thing, and you can see of all sorts of things that can happen. That's what I want to try and illustrate here. So with Lance Armstrong recently admitting his steroid use, granted this is an older problem, the drug testing committee for the Tour de France has decided to impose a ban for all of the cyclists receiving a positive test for steroid use. The percentage of cyclists in the Tour de France that take some form of steroids is 2%. Given that a person uses steroids, the chance of positive test for a steroid usage occurs as 99%. The downside to this testing comes from a false positive test occurring. What that means is basically a person is not taking steroids, but the test shows that they are taking steroids. So this probability that a person doesn't take steroids received a positive test for steroids is 0.05%. Unfortunately, such a result will mean these cyclists would also be banned from the Tour de France. Use this information provided to determine the probability that a cyclist will be banned. Okay, so how the heck do we do this? Well, this is conditional probability, and I'll show you how they work, and then I'll show you kind of a nice route to get there with the multiplication principle, because that's essentially what we're using, is a multiplication principle for a problem. So, first piece of information, the percentage of cyclists in Tour de France that take steroids. So, let me put probability of taking steroids. Let's say is 0.02. Now, from that, you can actually also get the probability of not taking steroids. That's immediate. And the reason why we can say this is immediate, probability rules, right? This should equal 1 minus 0.02, which is 0.98. Okay. Now, on top of that, we have some other information. Given that a person uses steroids, notice that keyword given. That is telling you it's a conditional probability. So given that a person takes in steroids, the chance a positive test for the steroid. So let's put plus test. So for positive test, given that they are taking steroids, is 0.99. Now that means also a negative test, given that they're taking steroids, is 0.01. Hopefully that you can decipher that. Now on the other side of things, we have a person did not take steroids, received a positive test for steroids is 0.05. So on the other side, you have a positive test given that they're not taking steroids. Equals 0.05. So we have a lot of false positives there. Okay. So now what do we want to find? We want to find the probability that a cyclist will be banned from the Tour de France. What I often tell people is to draw a tree. Now I'm going to draw a sideways tree, but hopefully that'll make sense in terms of what's happening here. So the first choice that the athlete has, or the route of the athlete, is either they're going to take steroids or not taking steroids. Okay, so Think of it this way. The probability that they take steroids is 0.02. I'm going to put that 0.02 right here. The probability that they're not taking steroids is 0.98. We found that right over on this side. Okay. Then it's out of the athlete's hands, but there's two possibilities from there. There's either a positive test or a negative test. For the positive test, if the athlete's taking steroids, there's a 99% likelihood that they end up with a positive test. Whoa, that was quite loud. Sorry about that. So then the negative test, notice that means just go 1 minus, that's 0.01. Okay. So now for not taking steroids, the sad side of this is that some people do get positive tests. Not all tests are perfect. In fact, there's always going to be some sort of error involved. And so notice that makes 0.05 here, and then our negative test is 0.95 in this case. I'm going to change colors up real quick and kind of illustrate what we want. So remember, this said impose a ban for all cyclists receiving a positive test. Use this information provided to determine the probability that a cyclist will be banned. Okay, so banned, technically all that is just a positive test. So now how can we determine the probability of positive tests here? We only have conditional probabilities. Well, it's actually not too bad at all. All you have to do is look at the routes. So we go taking steroids to a positive test. That's one route. And then we go not taking steroids to a positive test. That's another route. Okay, we can use our multiplication principle, and we're going to actually take these different routes and add them up. So we're using a multiplication principle and an addition principle. And so hopefully you can see, though, now I'm using drug tests here. Does it have to be drug tests? No. This can be a pretty important thing. Think of like detecting cancer and things of that nature. You have to know there's going to be some likelihood where we actually catch it and some likelihood where we don't catch it when it exists. So these things, these probabilities come into play, and conditional probabilities are the types of things we're going to want to use often. Okay, so the probability that a positive test occurs, all we need to do is, and I'll actually write out in words what's happening, and then I'll actually show you just from the symbols. It's a lot easier. So the first scenario, I'm going to try and abbreviate so I can fit it here. Taking steroids, I'll put take ST times the probability of a positive test. I'll just abbreviate with positive, given that they're taking steroids. Okay, so that's the probability of the positive test when they are taking steroids. Okay, now we want to add that to the other scenario. So this is an addition principle. Probability of not taking steroids times the probability of a positive test given that they're not taking steroids. Okay, so what actually happens here, and that's the multiplication principle basically for each part. We're using multiplication principle, addition principle because it's between two different parts. Here's how simple it really is. We just, after we draw a tree, you just take our 0.02 times our 0.98, or 0.99, my apologies there. And then we're going to add that to the other scenario. It's going to be 0.98 for our probability that they aren't taking steroids, times our probability 0.05 of a positive test when they aren't taking steroids. And this, just summing those, multiplying those and summing them, that actually gives us our answer. So you can get 0.02 times 0.99 plus 0.98 times 0.05, and so you get our final answer here is 0.0688, or 6.88%. Did it want a probability or a percent? Okay, probability. So we want a number between 0 and 1. There we go. That's it. Questions on that? I know that's a bit tricky, but hopefully the tree will help you in terms of trying to see how this multiplication principle actually works. You're just basically taking what route gets you to the desired result. Okay, And we can up this game a little bit too to try and illustrate. I'll have another problem coming up. It might be next, as a matter of fact. Let's see. Yeah, it is this one. So we can add this. So this one's dealing with the death penalty. So innocent people receiving the death penalty has always been a topic of concern in law and society. In cases where the death penalty is being pursued, 87% of the defendants actually committed the crime for which they are being accused. Of those guilty defendants, 93% are actually convicted and put to death. Meanwhile, the remaining defendants that are actually innocent can be wrongly convicted. The percentage of innocent defendants being put to death is 4%. Use the aforementioned information to determine the probability that a person given the death penalty is actually innocent. So, this is actually another problem. I mean, obviously, you never want to have innocent people being put to death. So we have innocent, probability that a person is innocent, where they are given the death penalty. Okay, so from the standpoint of what our probability rules state, we're going to need to find the probability that the person is innocent and given the death penalty. And we need to divide that by the probability that the person, or probability that a person is given the death penalty in the first place. Okay, so from that, we have this whole little blurb here. So we're talking about cases where the death penalty is being pursued. So you have two sort of scenarios here. 87% of the defendants actually committed the crime. So what does that mean? Well, it means they're either innocent or guilty. So in terms of drawing our tree, if they committed the crime, they're technically guilty. So that means 87% of those. So we'll put a 0.87 there. And that means the remaining portion would be innocent. And this is our first step, 0.13. And you can see from there, of those guilty defendants. So you're given guilty defendants, that is 93% are actually convicted and put to death. So this is the death penalty. All right, so you have 0.93. And so that means 0.07 will be no death penalty. Questions on the layout. That's really the tricky part of these, is kind of setting up the layout for these. And then on the other side of the fence, if a person is innocent, the probability that they're given the death penalty is the 4%. And the probability that they are not given the death penalty would then be 0.96. So now, how do we find these answers? Like, what are we actually looking for? So notice in our first case, we want innocent and death penalty. So here's how you do it. Innocent, and we want the death penalty. So we go right there. And so what are we going to do with those two in our branch? Well, we're going to multiply them. So you go 0.13 times 0.04. Now on the other side of the fence, we want death penalty. What's that probability? Well, notice innocent and death penalty is a part of the death penalty scenario. But then we want to also add in, we have another scenario, the guilty in the death penalty. Right? And so the guilty in the death penalty gives us 0.87 times 0.93. Okay? And so now we can actually take this and see what happens. So we take our 0.13 times 0.04, and we should get 0.0052. And then we can take that 0.13 times 0.04 and add that to 0.87 times 0.93, and I believe we get 0.8143. So double check me there. And so our final answer, what is this likelihood of this occurring? Well, ideally it would be 0, but unfortunately it is not. It's 0.0064. So 0.64%. Okay. So, but hopefully you can see how these things work out. Now, notice I didn't write out like what this probability is. So notice you have the probability of the death penalty given guilty equals 0.93. Right? You have a list of probabilities of that sort. Right? We could write it down all those, but if you use the table and figure out, okay, what do I need to find? That tree, I should say, the tree diagram. I find that to be a lot more useful for a lot of people. Not saying you have to use it, but it just tends to work a lot more efficiently. Hopefully that makes sense on the conditional probability. I know a lot of people were struggling on that. That's why I gave multiple problems in multiple different scenarios there. So hopefully you can see how that stuff works. Okay. All right. So now I know this one might be a little bit harder to read. So I will read it out just so you can see it. So it says, considering the following game of chance based on the spinner below. Each spin costs $4. If the spinner lands on A, the player wins a penny. If the spinner stops on C, the player wins $7. Otherwise, the player wins nothing. Okay. So now, I want you to calculate the player's expected winnings. Express your answer to at least 3 decimal places in dollar form. Okay, cool. So here's your outcomes. We'll put our outcomes down here. And the probabilities right here. Okay. So now I'm going to put off to the side A, B, C, and D, but those are technically not our outcomes. Our outcomes are the amount of money that's going on, to be honest with you. So outcome A, well, I mean, you can consider them the outcomes, but the outcomes in terms of a dollar amount is what we're really concerned with. So A, notice what happens. A, the player wins a penny, so that would be 0.01. Now, what's the probability of landing on A? 1/2. What's the outcome associated with B? Well, B, if you notice, there's nothing about. It says otherwise the player wins nothing. So that has to be, we spend $4 to play this game. So this would be -4. And the probability of landing on B would be 1/6. Okay. Same thing with C. We can figure out what happens on C. The C, the player wins $7. So we'll have $7 there. And the probability of landing on C is 1/6 as well. And then D, the probability of landing on D would be 1/6. And notice this one, it says it's an otherwise case, so they win nothing, so that means they lost $4. Now you might say, oh, player wins a penny, maybe you subtract the $4. No, we're just saying they win a penny, so they get $4.01 back here. Okay. So we are looking for an expected value scenario. And just to distinguish, since we have a couple different probabilities, I could combine those and make it easier on ourselves, but we'll avoid from doing that. Now remember, this is at sum x p of x, or I could use the calculator and punch them in that way. That's fine as well too. So I will actually write it out just so we can see where that comes from. If it gets a long list, that's when I will use something else. But when there's only 4 things, it's not too bad. So here's all you have to do. This is, you take the outcome, 0.01 times the probability that x equals that outcome. Since we have different probabilities, I'll use A's, B, C, and D here, times that probability that x equals A. Then plus the, what's the next one? -4 times the probability that x equals B, plus 7 times the probability that x equals C, plus -4 times the probability that x equals D. Okay. So now, probability that x equals A, we already said. So what do we have? We had 1/2 there. Plus the probability that x equals B, we have 1/6 there. Probability that x equals C, we have 1/6 there. And then the probability that x equals D, we have a lot of 1/6, I guess. Okay. And so now it's just time to plug and chug. So you take that 0.01 times 1/2 plus our -4 times 1/6 plus our 7 times 1/6, and then last but certainly not least, our -4 times 1/6. So notice what happens. Well, it wants us to round our answer 3 decimal places in dollar form. Okay, so overall you get a negative number. Now that makes sense because negative numbers are a possibility here. So we have $0 and what do we have? 162 would be our rounded to the nearest decimal place. So notice overall we'd be losing money. And guess what happens when you play in a casino? Usually your expected value is going to be negative. So that makes sense, and that's usually what happens. That's what they're banking on. Okay. Over time, there's a law of large numbers there that occur. You're going to lose money in the long run. Doesn't mean you can't win money in a short run, or how long is or how large is a large number is another thing that comes into play. But basically, you can start calculating these odds, and you can see the payouts versus what you're paying in. They really don't bode well in the long run there. So, questions on that? Alright, so now for the next one, I wanted to try and follow that up with something that's more calculator based. We have our x and we have our p of x, and we want to calculate the mean, the variance, and the standard deviation. Well, when you take a look at this one's screaming to you to use a calculator, so we'll go ahead and use it. If I can move it, oh come on. There we go. Alright. So, let's clear that out. So we want to go and make a list. And we will go over here, clear this out. And then we'll go over to our right one. Now I could put them in list 3 and list 4, and I'd recommend doing that. I just like to be consistent though for when I'm displaying stuff. List 1 and list 2, it's easier for people to remember and all that jazz. So, and you saw how I cleared them out too, by the way. I just went up, I hit clear, and then I hit enter, and it clears out the whole column there too. So remember our first one, we go and we just punch in our possible outcomes. So -4, 6, 9, and 8. And granted, this one is short, but we can do this pretty quickly too. And then our probabilities are 0.581, 0.104, 0.205, and 0.11. Okay, now from there we go to stat, go to calculate the one var stats, and then we can click our second L1, second L2, hit enter, and then we got a lot of our important information for us. This x bar is 1.025, and I'll put that in. Now we could have done that the old-fashioned way, the sum of x times p of x. Remember, that's the same thing. So this would have been the summation of x times p of x. Now, here's why you kind of saw me take a shortcut. What happens is, so this is actually, and they use x bar in there. By the way, that's usually denoted by a mu. And that's an x. Don't let your eyes fool you there. Okay, then the next one is this sigma x squared. The way they go about doing that, that formula is not nice, and that's why you don't see me writing it down. This becomes x minus mu of x, the quantity squared, times p of x for each value. So what we'd have to do is I would take, for example, x minus mu of x, if I wanted to do that, the quantity squared, list it right here. I would have to do, in our first case, I go negative 4 minus 1.025, and then I square that value. By the way, rounding it, I also shouldn't round it, but I will here just so you can see what's going on. That's 25.25 in the first case. Then when I take 6 minus 1.025, and then I square that number, I get 24.75. And I'd have to take each of these and multiply by the probability. That's one method. That's going to be quite tedious, right? Well, the easier way, and by the way, that's the variance is just the standard deviation squared. So we take the square root to get the variance. So when you look as to what's happening, let's go back to that calculator once more. And so notice we have our sigma x is already done for us. It's 5.9694, yada yada yada, right? So I can write down the 5.9694 or 5.9695, right? Right in here. Already taken care of. Now, when it comes to the variance, rather than going through that whole calculation, which you can, it can be done, I just highly recommend not doing it. Oh, so I see a question to tie into that previous problem. In the previous problem about the expected winnings, can the TI-84 be used to plug in the numbers? Is the answer the same as the mean? Yes, most definitely. And actually, I'll go back and show you just to make sure we get that across. So great question, Lauren. Most definitely. And I'm just trying to illustrate a couple different ways to kind of go about doing that. So for this one, what do we have?